Hello everyone, and welcome to the third session of this set of videos created to explore programming applications in reinforced concrete. In this third session, we will be using Maple again, but this time to explore a Maple document that is created to perform flexural analysis of flanged reinforced concrete beams carrying positive bending moment. A flanged beam has a flange and a web, where the flange is usually part of the slab system and the web is the drop of the beam below the slab. If the beam under consideration is intermediate and has slabs running on both sides and is cast monolithically with the slab, the beam will have a T-shaped cross-section. But if the beam is an edge beam where slab is present on one side only, the beam will have an inverted L-shaped cross-section. Today we will deal with flanged sections carrying positive bending moments, as we will deal with those carrying negative moments in another session. Positive moment means that the rebars will be placed in the web and the compression zone will be located at the top of the cross-section. The compression zone can be rectangular in shape when entirely located within the flange, and thus the flange section can be treated as a rectangular section with constant width equal to B effective. If the Whitney equivalent depth of the compression zone exceeds the thickness of the flange, the compression zone will have a T or L shape and the cross-section will require a different set of equations to calculate the design strength from those used for a rectangular section. When performing flexural capacity analysis, the difference between the solution procedures of T and L-shaped cross-sections is in the calculation of B effective. Let's check the Maple document that I created to perform flexural analysis of flanged reinforced concrete beams carrying positive bending moment. This here is the zone where the user inserts the required input parameters, which are depth of beam, thickness of the flange, width of web, yield stress of steel, modulus of elasticity of steel, compressive strength of concrete, number and diameter of bars in the layer farthest from the neutral axis, number and diameter of bars in the second layer, concrete cover, and the diameter of stirrups. These two parameters are used to calculate the effective width of the flange according to the ACI code procedure, and these lines give the user the option to analyze a T-shaped cross-section or an L-shaped cross-section, where 1 indicates a T-shaped section and 2 indicates an L-shaped section. I have selected the numbers shown on screen in order to be able to demonstrate the cases that I want to show you. So if we run here the first analysis, Maple will produce the required results. Here you can see the analysis with the output parameters. The user have requested the analysis of a T-shaped cross-section. Maple checks the depth of the compression zone and indicates that the depth of the compression zone is actually larger than the thickness of the flange, and thus this beam will have a non-rectangular compression zone, calculates all the required parameters, checks whether the section satisfies the ACI code or not, and since it does, it calculates the design strength phi times Mn. Maple then plots the cross-section, shows the ductility status of the beam, and shows the depth of the compression zone. Let's change some of the numbers here. Let's change the thickness of the flange to 120 and run the Maple document again. You can see that Maple performs all the calculations, prints the cross-section, shows the ductility status, but this time the depth of the compression zone is actually smaller than the thickness of the flange. Therefore, this T-beam can be analyzed as a rectangular beam with a constant width of B effective. If we go back to the input parameter zone, and change the input parameters in order to analyze an L-shaped cross-section. I will use the parameters inserted on screen, and note that here I've indicated that I want to analyze an L-shaped cross-section. Let's run the Maple document. Maple produces the required results. The user has indicated that the shape is to be analyzed as an L-shaped cross-section. Maple checks the depth of the compression zone and decides that the depth of the compression zone is actually greater than the thickness of the flange, and thus we have an L-shaped compression zone. Maple calculates all the required parameters, checks whether the section is adequate or not, and prints the design strength. Again, the cross-section of the beam is plotted. The ductility plot is also shown, indicated that we are in the tension control zone, and then the depth of the compression zone is demonstrated here on this figure. If we go back to the input parameter zone and change here the thickness of the flange to 120, change here the diameter of bar to 25, and run the Maple document, we will see that the section has a rectangular compression zone. It is adequate, it satisfies the ACI code requirements, and it has a compression zone that is rectangular in shape. So this beam here can be analyzed as a rectangular section having a constant width equal to B effective. If we try to jam the cross-section with more steel, to 70, change the thickness of the flange and run the section again, you will see that Maple shows that the steel that has been added is too much. The section is now in the transition zone, and thus Maple does not plot the shape of the cross-section or the depth of the compression zone because it is irrelevant. The shape does not satisfy the ACI code requirements. This concludes this session. Thank you very much for being with me again, and hopefully I will see you in the upcoming sessions. Best wishes.